going to do samples 10-4 and 10-5 on the same video because I think that the comparisons are worth it. So the titles are rotational inertia for barbells 1 and rotational inertia for barbells 2. So we're going to talk about a thing called a barbell today, which is basically two heavy weights at the end of a light bar, which is long compared to the radius of the masses and light compared to the weight of the masses. So basically we can ignore it except for its length. So we're going to mess around with a few things. In all three of these samples, all the masses are equal. M1 equals M2, they're 50 kilograms. So we're going to keep that constant and we're going to vary a couple of things. One of the things we're going to vary is how long the barbell is. And then another thing that we're going to vary is where does it rotate about, right? What's the center of rotation? And so we're going to see how the moment of inertia or the rotational inertia varies based on, like I said before, how long the bar is and what axis you rotate it about. And in the first sample, we'll just calculate the rotational inertias. And in the second example, we will actually calculate kinetic energies. But as you know, once you have the rotational inertia, calculating the kinetic energy is quite simple just using that formula. So I'll erase that for now. So we'll start with sample 10-4. In the first example, the two masses are separated by 1.20 meters. Okay, that's the length of our bar. And since we've said that the bar is long compared to the radius of the masses, we don't have to add one radius of each mass in there or anything like that, like we did with planets. So this makes it a little bit easier. Now we're going to rotate around the center of this. So if you could picture this in 3 dimensions, one of the weights is coming towards you and the other one is going away from you, and it's rotating in the plane, in and out of the plane of the whiteboard here. And if you look at the picture on page 456, you should be able to make some sense of that. So what's the moment of inertia or rotational inertia here? So to find this, now we've got two objects, so our summation makes a little bit more sense, right? M1 times R1 squared plus M2 times R2 squared. This is very similar to how we did center of mass, right? The radius wasn't squared, but when we summed them all up and we added everything together. So the masses are the same and the radiuses are the same, but let's just be explicit. 50 kilograms times, now this is 0.6 meters because we're halfway, right? This is the distance we're looking for here. And that's squared plus another 50 kilograms, the other mass, which is also 60 centimeters away. And we have to square that. And we get 36 kilogram meters squared. So that's the rotational inertia of this situation. Rotated about its center of mass, okay? Part B says, well, what if they're separated by 2.4 meters? Well, now I've got a longer, right? Not to scale here, but we've got a longer barbell, and we're going to, again, rotate around that center of mass, if you will. So, again, the sum of all the m's times all the r squareds, right? Now, we know we've got symmetry here, so I can say 2 times, right, 50 kilograms times now I'm 1.2 meters away squared, right? And there's a few ways to get this answer, but the answer is 144 kilogram meters squared, okay? What happened when we doubled the radius, when we doubled the distance, what happened to our moment of inertia, our rotational inertia? It quadrupled, right? So we're always on the lookout for if this changes, how does this change? So this might be getting obvious for you, which is awesome. Looking at this formula here, if I double the radius, then we square that and we get a factor of 4. So it shouldn't be too much surprise that doubling the distance between those masses resulted in a factor of 4 change for the rotational inertia. So that essentially is sample 4. Now going on to sample 5, which is just on the next page, now we've got this larger barbell again, 2.40 meters. right? And we know the rotational inertia around the axis here, this axis is, I forgot, 144 kilogram meter squared. But what if I want to rotate it around one end? Okay, because I could do that. I could hold one of the barbells and whip it around if I were strong enough to do that. What if my axis is here? Okay, so I've got to do my same sum of all the m's and the r's squared. But now there's no symmetry here because the two barbells are not the same distance from the axis. So I got to do each one. M1 R1 squared plus M2 R2 squared. But M1 is right here at the axis. So that first term is 0. It is 50 kilograms, but it is at the axis. So the distance between it and the axis is 0. And so when we multiply this, we get 0. Now, what about our second mass of 50 kilograms? Well, now it's 2.40 meters away, and we have to square that. Okay, and the rotational inertia that we get here is 288 kilogram meter squared. And this is sort of counterintuitive at first because you might think, well, yeah, one's twice as far, but one is right on the axis. So you kind of think it might cancel out, but it doesn't, in fact, okay? Same mass, but we've moved the axis, we multiplied that moment of inertia by 2. And this isn't really a factor of change question that you could be expected to figure out, but we could calculate it, okay? And if you think about it, like pick up something like next time you're in my classroom, pick up a meter stick and try to spin it around the center and then try to whip it around by one end. It's more difficult to do that way. And that's why. It's all because of rotational inertia. So we get a lot more difficulty in rotating stuff about one of the axes rather than the center. So that was the first part of sample 10-5. Now we're going to determine the kinetic energy of the barbell if it rotates at 1 radian per second about the midpoint, and what if it rotates around the end. So let's be clear because we've got a lot of parameters going here. Let's do kinetic energy rotating at, what did it say? 1 radian per second. Sorry, I don't know what that does. Radian per second about the midpoint. Okay, so I've got to get so K equals 1/2 I omega squared. So I've got to go back and figure out what I was about the midpoint. It was 144. So 144 kilogram meters squared. And then we multiply that by 1 rad per second. Quantity squared. Sorry for that scribble. And what do we get? 72 joules. So that's about the midpoint. What about rotating about the end? All right, so K equals 1/2 I omega squared. Our 1/2 is the same. Our moment of inertia around the end was 288 kilogram meter squared times 1 rad per second. Quantity squared gives us 144 joules. So that shouldn't really surprise you. We're looking from a factor of change method. The moment of inertia, the rotational inertia doubled. The angular speed stayed the same. So the new kinetic energy is twice the old kinetic energy. This is very similar to saying, well, if I give a soccer ball a certain speed, what's its kinetic energy? And then I've got one that's twice as heavy, has twice as much kinetic energy. So the analogy between rotational inertia and inertial mass holds up. So I'm sorry for the long video, but I think that was the best way to combine both of those examples, and I hope they helped.